really helps to know what we're looking for and know what we can expect to find. So in general, what we're looking for are supermassive black hole binaries, because this is one of the potential sources of nanohertz gravitational waves and ones that we think will be the strongest. So these are formed in the aftermath of galaxy mergers. So if two galaxies interact and end up merging, their stellar cores will merge, and then eventually the supermassive black hole binaries in their center will start to interact and then someday form a binary. And then someday, these supermassive black hole binaries will eventually emit these low frequency gravitational waves that we're trying to look for. And these can include both continuous waves from a single binary. So these are things that as a single binary is orbiting, we'll have a nice discrete sinusoidal signal that we'll know and be able to model and then look for within the data. And there's an example down here, and you can see as it's wiggling predictably as the binary orbits. But there's also things like the stochastic gravitational wave background, which we expect to be basically the summation of all the possible gravitational waves from supermassive black hole binaries everywhere throughout the universe added together. So rather than modeling all of those possible sinusoidal signals all together, instead we model this as a red noise process and look for it within all the pulsars at once, which we expect this to be a stronger signal than some others, but this can be really difficult because it's not exactly determined. But of course, in reality, life isn't perfect, and all of these signals are actually in the data all the time, all at once, on top of all the really complex noise that exists within the data set. So we need to be really smart about what we're looking for and when we're doing it, and making sure that we're not getting confused between other possible things. So first, the first search that you might hear about from nanograv is for the gravitational wave background, since we expect this to be the strongest source of nanohertz gravitational waves in our data. So I'll quote here, as I've recently heard a talk about how to describe this. So the gravitational wave background is expected to appear as a spatially correlated common spectrum red noise process. And it's a very exact term, so I can break it down a little bit. So the common spectrum describes the red noise that is within all of the pulsars that we expect to be due to the gravitational wave background. And this has a determined spectrum based on the source. Here, we're expecting to look for supermassive black hole binaries, and that spectrum can change depending on the source that we're looking for. And it's common to all of the pulsars. So the pulsars have their own red noise intrinsically from things like the spin noise or the interstellar medium, but we're looking for any noise that might be the same, because we might expect this to be from a gravitational wave rather than the pulsars themselves. The spatial correlations are a little bit more subtle, but the general idea here is that the degree of correlation of that common spectrum red noise depends on how the pulsars are distributed in space. So pulsars that are very close together might be strongly correlated and the noise might look more similar. And pulsars that are farther apart might have noise that looks a little bit more different or even anti-correlated. And you can see a description of that degree of correlation here as pulsars are both close and far apart, and this is called the Hellings and Downs curve. So in our most recent 12.5-year data set, we're not yet seeing evidence of that spatial correlation. As you can see by these orange points here, they're not quite following that curve yet. But what we are starting to see is strong evidence of an uncorrelated common spectrum red noise process. You can see a posterior describing that down here. So while we're not detecting the gravitational wave background yet, we are starting to detect some common noise, which could make things really interesting in the future. This will also start to complicate some of our other gravitational wave searches. And this includes searches for continuous waves, which are the deterministic signals from the individual supermassive black hole binaries that we're looking for. So typically when we do this, we search for continuous waves across the entire sky and at all possible frequencies. So over time, we're starting to get more and more sensitive to continuous waves. You can see by this set of upper limit curves starting to creep on down as we add more data. So this is good. However, we don't really expect to detect one of these until we can start to detect the background, since we expect to detect the background first. However, one of the reasons this can be really difficult is because they're very computationally expensive. So each point on each of these curves is actually from a separate gravitational wave search. So we need to separate out all of these curves into their individual frequencies and then search them individually. So many, many searches need to be done to construct one of these curves and make sure that what we're looking for is a continuous wave at any given frequency. This is also made more difficult because we're not equally sensitive to sources across the entire sky. So all of the stars on the sky map are pulsars from the 11-year data set. You might notice that there are a lot more of them on this side of the sky than there are on the right. If we divide up the sky and then do gravitational wave searches just within each little bin on the sky, you'll notice that we are not equally sensitive with it as on one side of the sky where all the pulsars are as we are on the other, due to that distribution of pulsars. So the yellow on this color map is indicating we have more sensitivity. We can see a given source a little bit farther. So for example, for a supermassive black hole binary emitting at 8 nanohertz and having a mass of about 10 to the 9 solar masses, we could see that source out to about 120 megaparsecs on this left side of the sky. However, on the right side of the sky, where this color bar is more purple, we could only see that source out to about 20 megaparsecs, which is a big difference. And the upper limits are similarly different as we're looking in gravitational wave strength. So this can really complicate things. Plus, as I mentioned before, we're starting to see some common red noise in our pulsars that we're not exactly sure what it might be due to yet. So as we're looking for these continuous waves, we're starting to need to take that into account. So here I'm showing again these green, orange, and blue curves that I showed before as our upper limit is creeping on down. And then I've also added some red and purple curves on here for the 12.5-year data set, which is the most recent nanograv data set. And you'll notice that instead of just having one curve for this data set, there are actually two. So these are, again, sky averaged upper limit curves calculated at every frequency across the nanohertz band. But in one of these curves, we've actually included that common red process. And you'll see that down at these low frequencies, it's starting to make a difference. So we really need to start being smart about what we're looking for and taking other things into account. So as we're thinking about this, it's also important to think about the context where we're looking for supermassive black hole binaries. So we know that supermassive black hole binaries can emit fairly stably for a very long time, and they can be within the PTA range for a very long time, as you can see on this little timeline here. But supermassive black hole binaries have a very long history by being such stable sources, and we're still trying to figure out exactly how to detect them electromagnetically and be able to match that up to the possible gravitational waves. So from steps all the way from a possible galaxy merger and on through the process of emitting continuous gravitational waves, there are a lot of steps within there, and there are a lot of possible markers that we can use to look for these sources. So for example, just to list a few of them, for example, think about what if we saw a post-merger galaxy that looked like it had been disturbed. This might mean that the galaxy had recently interacted in its past, but by some point in time, it may have settled down enough to have formed a binary within it. If, for example, we were tracking the brightness of, for an example, an AGN, as you can see up here, and we saw some kind of periodicity in there, this might indicate there might be some motion that might be hinting at a supermassive black hole binary lying in there. If we are doing some astrometric tracking of AGN and seeing whether they're in the same place all the time, if we see some kind of periodicity in that, so perhaps some kind of orbital motion in there, this might indicate a binary. We may actually see two cores in an AGN, so a dual AGN. And this, so far, is the only unambiguous way to identify a possible binary yet. And there's a ton of different spectroscopic evidence that we can use, such as looking for dual offset broad lines where the hot gas and dust in an accretion disk is moving around according to binary motion. So to start, I'm going to focus in on this bottom right plot here. This is actually a plot of 3C66b, and it's sort of the study that started it all. So here, I'll change gears a little bit and start talking about this project that we used to look at 3C66b specifically. So in case you haven't heard of the source before, I'll step through a little bit of its history. So in 2003, a supermassive black hole binary was first proposed by the pseudo group via that orbital motion that I showed. So this also came with a very specific orbital model with an associated mass and orbital frequency. In 2005, this was actually ruled out via pulsar timing. This pulsar timing study was a little bit special in that it only used one pulsar, and it was more of a Fourier analysis where they basically made a periodogram and were looking for any excess power in any given gravitational wave frequency. And they were unable to find any. So what they were able to say was that there was no evidence within their pulsar data that matched with the 2003 orbital model. So it was able to be ruled out. However, in 2010, there was actually a revised model published by the same group with a different lead author. And this study actually looked at flux variations and was able to match those variations up to the original orbital frequency from the 2003 study. However, they revised their mass. So they said that actually a much lower mass fits with the supermassive black hole binary, and that would have been unable to be ruled out by that 2005 study. And to date, this mass has not yet been ruled out by pulsar timing. So this is what we did. We decided we wanted to use the full pulsar timing array with the full gravitational wave model to go and look at this source and see what we could say about that 2010 mass. So this orbital motion that was discovered in 2003 corresponds to a gravitational wave frequency of 60.4 nanohertz. And this lies very nicely within this nanohertz PTA regime. So this is exactly what this is exactly the type of source that we would want to be looking for. It's a great target for us to look at. And this error bar, this plus or minus 1.7 nanohertz, is very low compared to the frequency resolution of our PTA. So essentially what we can do is take this as a given target frequency and look directly there. We can say, okay, we know where the source is on the sky. We know what frequency it's emitting at. Let's go look for it. And that's exactly what we did. So we started off with our with Nanograv's premier search software named Enterprise, and then follow that up with a Markov chain Monte Carlo analysis. So Enterprise is basically what we use to construct our likelihood, and then we sample it with the MCMC. This can be very difficult, particularly for continuous waves. So for continuous wave searches, there are 4 parameters that go into the search per pulsar, plus 7 global parameters that describe the continuous wave. For the 11-year data set that we used for this search, this totals up to 179 search parameters, which all we can really say is yikes, it's a lot to do. However, if we're smart about this and use some multi-messenger techniques, which is what we wanted to do here, we can actually reduce the number of these global parameters. So for example, for this method right here, we know where our galaxy is, so that's 2 parameters to describe the sky location, and we know a distance to the source, so that means we can take out 1 more parameter and then search directly in chirp mass. So this is what we did, just to try and make our lives a little bit easier. So spoiler, we didn't actually detect any gravitational waves from 3C66b. You can see a posterior from our detection run on the upper right here. So there's a Bayes factor calculated from this run of 0.7. This means there's no evidence for a signal in the data. Because of this, what we can then do is an upper limit analysis, and you can see a posterior from that run down here. And when we calculate an upper limit from this blue posterior histogram, we calculate an upper limit of 1.6 times 10 to the 9 solar masses. While this is the lowest upper limit that's been set on this source, it's unable to rule out that existing 2010 model, which you can see plotted in this orange region right here. So while we're getting close, we're unable to rule that out yet, and it's still consistent with the data. What we are also able to do is take that upper limit and compare it to the 11-year continuous wave search, which was an all sky search. So here we're trying to see how much that multi-messenger information of knowing a specific source to look at was able to help us. And we can see whether we were able to do a little bit better. So we can go look at the sky averaged upper limit at 60 nanohertz in the closest frequency bin to 3C66B's frequency, and convert that value to a chirp mass and see how close it is to our value. Also, what we need to keep in mind is that 3C66B is in a fairly insensitive part of the sky. Remember that our sensitivity is not even over the entire sky. Because 3C66B is on the side on the right, you may hear people speak about it colloquially as the bad side of the sky, where it's fairly insensitive. So we might expect that even though we knew where we were looking, we might have done worse than the sky average, since it's a little worse than average. However, we actually did better than the sky average search. So we have a lower upper limit on this targeted search than on the all sky search at the same frequency, even on the bad part of the sky. So this is really great. This means that as long as we know where to look and we have a source in mind, we might be able to do a little bit better than just searching the entire sky at once. So this is really good news. What we also wanted to do is directly test that 2010 model. And you can see an example of how we did that here. So the orange curves for both on the left and right here are both priors on both the log chirp mass on the left and the log frequency on the right. You can see that the blue posterior for the log frequency basically exactly returns that prior. This means that no information has been gained about possible frequency for 3C66B, which is exactly what we would expect since we didn't detect any gravitational waves from it. However, when we look at the chirp mass posterior, you'll see that it doesn't exactly match this orange prior. This means that we were able to gain a little bit of information about the possible range of masses that is consistent with the data. So this is good news. Even though we didn't detect anything, we were able to gain a little bit of information about this model. So what we wanted to do next is really kind of broaden our search and think about how we would do this for any other sources where we don't have as an exact of measurement for the gravitational wave frequency. So what if this error bar on this frequency was a little bit bigger? And what this would equate to is how would we search for a candidate that has a more uncertain orbital model? What if we didn't know that model very exactly? So what we decided to do was, instead of searching one frequency, we decided to search it directly and sample over many frequencies in a single run. This is the first time it's been done on the full PTA of sources and on real data. And what's great is that this actually works very well. So you can see here a 2D histogram where the x-axis is log frequency and the y-axis is log chirp mass. And most of these 2D histogram bins have about the same number of samples in them. That means that the sampler is not preferring any one region of parameter space, which is good because we know from our detection run, we don't expect there to be a gravitational wave in here that we can detect. So it's able to move over the space smoothly, which is good. However, there is this upper right corner where there are no samples. This means it's able to rule out this area of parameter space. What this means is that if we bin up these frequency bins, so as we step through along the x-axis, we can take an upper limit for each of those bins in chirp mass, and then calculate an upper limit curve for chirp mass within one run, rather than doing all of these frequencies separately. So this is really good because it can be a little bit faster, and we can see that it works just as well at this frequency of 3C66B, where the orange dot or the orange triangle is the upper limit for a single frequency run. We get just about the same value if we're sampling frequency as if we're not. So this is good news. It means it's working. What we can then do from this is we can convert this plot into a curve that shows how the upper limit evolves as we include more and more frequencies in our search. So here what we're doing, if we start at the frequency of 3C66B and calculate that upper limit, that's this point right here. And then as we include more and more of those points, we'll move along this curve. And what you'll notice is that this curve is very flat at the left end. So it's not until we include about an order of magnitude in gravitational wave frequency that our upper limit starts increasing. So this is really good to know, because this means that we can effectively search for most sources on the sky as long as we know where on the sky to look. Because we can search over the frequencies fairly well, we don't need an exact value of the frequency to make it worth our efforts to take a look at the source. Just in case my hand and mouse waving didn't quite get that idea across, I have a little animation here. So the blue star on this curve corresponds to taking all of these samples within this blue region and calculating an upper limit for all of them. And then as we gradually widen that region here, we're moving to the right along this curve. And it's not until we include this entire frequency band that we actually lose the sensitivity and move all the way up here. And there's about an order of magnitude in trip mass upper limit difference here. So this, while it's a drastic difference to know where in frequency space to look, it doesn't need to be exact because we have this large flat space down here. So what this means, and what I hope you take away from this discussion, is that the pulsar timing array really can do astrophysics right now, even though we haven't detected a gravitational wave background yet, and even though we haven't detected a continuous wave yet. We can really start setting meaningful astrophysical limits, not just on 3C66b, but on other sources that we haven't even looked at yet. So if you have a particular favorite, definitely keep that in mind and feel free to get in touch. If you're interested in taking a look at this, I put some QR codes to both the 3C66b paper and a Jupyter notebook we put together that teaches you how to remake the plots from the paper and analyze data like this. So I'll show these again at the end of the talk just to make sure you can grab them, but absolutely feel free to take a look. So now I'll change tack a little bit and talk about my current project that I'm working on with Steve and Maria Carisi on AGN variability and looking for supermassive black hole binaries within these variable light curves. So now, rather than talking about this orbital motion example, now we're going to change tack a little bit and talk about this example of a variable light curve and looking for supermassive black hole binaries within light curves like this. So what's great is that there are a lot of AGN surveys, and so there are a lot of candidates like these, and I'm just showing a very small number of them here. So this is a really rich area for us to start looking for possible targets in. And they make really great pulsar timing array targets. So this is a plot from a recent paper by Chungchung Jin showing a bunch of Catalina real-time transient survey periodic candidates here on against future pulsar timing array sensitivities. And you can see they fall nicely on this plot, and we should someday be able to detect a few of them. So these fall right within the nanohertz gravitational wave band, so right where we hope to look within pulsar timing array data. And they actually lie in a very sensitive part of the nanohertz gravitational wave band. So you may have seen a simplified pulsar timing array sensitivity curve that looks rather wedge-shaped. And that tends to bottom out like just below 10 nanohertz. And that's right around where these like to lie. So we have a good shot of detecting these types of sources, which makes these a good type to look at. So what complicates matters is that AGN also have an intrinsic red noise process, and this can be described as a damped random walk. And this is controlled by two parameters, where one is sigma, so a variability amplitude, and one is a tau, so a variability timescale. And I'm showing two example simulated light curves on the right here, just showing how if we turn these dials of sigma and tau, how different the simulated light curves can really turn out to look. So here on the upper right, while there's clearly some noise in there, it doesn't look too complicated to look for any signal within there. But this one on the bottom here, by eye, we might almost say that that looks periodic. So just showing why this might be difficult, because this red noise process can make searching for any periodicities kind of difficult and confusing. So the main idea for what we're trying to do here is use Markov chain Monte Carlo methods to constrain both that damped random walk noise and any possible periodic signals in simulated light curve data. And the questions we want to try and answer are, what types of supermassive black hole binaries are we capable of discovering? And are there any types that we'll be likely to miss and that this method isn't probably going to be able to recover? And this is really important knowledge to know while preparing for continuous wave searches, as we start to be able to reach the sensitivities required to detect a continuous wave. And as we get ready to do more multi-messenger science, because we're going to need to be able to match up a possible continuous wave with a host galaxy. And this might be one of the ways that we can do that. So first, we need to make sure that we can constrain noise in these simulated light curves accurately. And this has been done before. I'm showing a plot by Kozlowski et al. That shows the recovery capabilities for a few different survey setups using a very similar method to the one that we use. So here, they're plotting rho, which is just the variability timescale tau divided by the length of the survey. So we can think about this as tau as well. So they're also showing rho input on the x-axis and rho output on the y-axis with a nice one-to-one line here in red. So for low values of rho or tau, they're able to recover the parameter very well, and it matches this one-to-one line. However, for large values of tau, they're not able to constrain that parameter just because within that survey length, they're not able to constrain it. And this goes for the more densely sampled light curves as well from on the right, where for low values of tau, they're able to constrain the value even better. But again, for large values of tau, they're not able to recover it. We're able to do basically just as well. So for low to middling values of rho or tau, we're able to recover it, see down here. But for large values, we are not able to recover it as well, and it's typically underestimated. So this is similar to existing setups, so this is good. So now we need to start thinking about the possibility of binaries, because the supermassive black hole binary, as I've said, can change the effects we observe in a variable AGN. So this might be due to something like, as there's some motion going on, there's some variable Doppler boosting or downshifting that might be going on. And this is what we're trying to look for. So as we're starting to add some sinusoidal signals in here, we're starting by describing them in simple parameters, so an amplitude, a period, and a reference time, but we'll eventually try and match these back to parameters of a binary itself. So here I'm showing again that simulated light curve, but now I've injected a sinusoid into it, and you can see that it looks periodic, yeah. But if we compare it back to the noise-only curve, again, by eye, it might be really difficult to differentiate between the models here. So we really need to be clever about how well we can recover all of the parameters here and whether we can actually differentiate between what model we want to fit to a simulated light curve. So as I said before, and I'll keep showing examples of this, the noise processes can replicate these periodic signals. So we need to be really clever about figuring out what's actually in the data. Here's a nice plot by Vaughn et al. That shows it very well. There's a random simulated light curve here in pink that only has noise in it. You can see that it fits both some data and a fit sinusoid very well. So we need to be very careful about this model selection. So what we start by is making sure that in a noisy light curve, we can recover sinusoidal parameters. And luckily, we're able to do that. So here I'm showing these in versus out plots again for both log period of the sinusoid and the amplitude. You can see, again, especially for these strong signals that we're starting with, they fall right along this one-to-one line. So we're able to recover sinusoids within these noisy light curves. What's also important is that we're still able to recover the noise just as accurately, whether we're searching for both the sinusoid and the noise, or we're searching for just noise. So again, for low values of tau, even if there's a sinusoid there, we're able to recover it very well. But again, for very large values of tau, even if there is a signal in there, we're not able to recover it as well, but it's just the same as it was before. What's also important to note is that this is also true if our simulations only have noise in them and we're searching for a sinusoid that isn't actually there. So these are the orange points here. So whether there is a signal injected or not, if we're looking for a signal and we're looking for noise, we can characterize the noise very well. So this is good. So another example of just how difficult this can be is here I'm showing on the left an input light curve with both the injected signal and the actual light curve that we injected, so the final data. And here I'm showing the reconstructed light curves from two different searching runs, one where we're looking for noise plus a sinusoid, and one where we're only looking for noise. And by eye, it's fairly obvious that the noise plus sinusoid model matches the data a little bit better. But you can see on the right here how the sampler is trying to make these noise parameters try and match the data that's input. In this case of a fairly loud signal, it is fairly easy by eye to look and say, oh, well, the sinusoid looks better. But in the case of a less loud signal, this can be more difficult. And these are the cases that we're really trying to look at and see where the boundaries are between what we can recover and what we can't. So the way we need to do this is by doing a consistent model selection. And the way we're going to do that is by calculating some Bayes factors from Bayes information criteria. You can see here I've plotted Bayes factors for the two different survey setups we're working with, one with a sparsely sampled light curve, one with a densely sampled light curve. And I'm plotting those Bayes factors versus the amplitude of the sinusoid. You can see that for very large amplitude signals, we're getting some nice to high Bayes factors in both cases. So this is good. What we can also do is then do this again for the cases where we're only injecting noise and then searching for a possible signal and see what we recover. And it's good to see that these orange points that only have noise in them are consistently returning low amplitudes and low Bayes factors. And it's good to note that in the case where we have more data points, these two populations are looking a little bit more separate. So the more data points we have, the more reliably we can select a model. So this is good. But it's really down in this region where they're overlapping that we want to be looking, because that's where we're going to be needing to test those capabilities and what's the boundary of what we can detect and what we can't. So now what we're starting to work on is using some more realistic data sets. So up until now, we've been working in evenly sampled data, which we know since life isn't perfect, we can't always get. So we're starting with some Catalina data to represent the current surveys and capabilities of surveys that currently exist. To represent things like data gaps and things like that. You can see an example of a simulated light curve with those realistic data timestamps here on the right. We're also trying to look forward to the Vera Rubin Observatory, which is going to really just be our new best friend. And because it's going to be able to survey the sky so regularly, so there's going to be some really great data coming out of this survey, which, as we expect, the more data we have, the more reliably we can look for any signals within this light curve, because we're going to be able to pick a possible sinusoid out of this light curve, which has many more data points than we would out of this light curve on the top. So what we're really going to start doing now is redoing all of these experiments for these more realistic survey setups, and then seeing what we can find. So the next steps for this project, we're going to start quantifying what ranges of parameters are actually recoverable, and exploring any parameter pairs to determine if there are any covariances and the capabilities and limitations of the search method. And this is what's going to tell us what types of supermassive black hole binaries we can expect to discover with the method. So this is really going to give us some knowledge about what types of electromagnetic data sets we need to search for in the event of a continuous wave detection. So if we detect something, depending on the parameters of that binary, we might need to know what electromagnetic data sets we want to look in and whether variable AGN is a good possibility for this or not. And we know multi-messenger astronomy is really a balancing act, and we need to get ready from both sides, both electromagnetic evidence of supermassive black hole binaries and gravitational wave evidence. And by thinking about how we're going to put those together now before we can do it, we're going to be better prepared once we hit the point where we can do so. So if there's anything you remember from this talk, I hope that you'll know that we shouldn't wait. We should really get going on things like this now, because there are so many exciting discoveries that are already waiting for us, and we need the time to make sure we can find them. But even though we haven't made a detection yet, pulsar timing arrays are really ready to start doing astrophysics right now. So if you have any sources you're interested in looking at, I will definitely urge you to start looking at them. I'll show these QR codes again for both the 3C66b paper and the notebook in case you're interested in grabbing them, or always feel free to just get in touch with me at caitlin.witt@nanograv.org. And thank you. I'm happy to take any questions.
That was great, Caitlin. Thank you so much. Any questions immediately for Caitlin? Jesse? Yeah.
Hey, thanks, Caitlin. That was a great talk. Have you started thinking about, or do you have plans to think about how different observing strategies with Rubin Observatory might impact your ability to pick out periodic signals?
That's a really good question. And I don't think we have thought about that yet, but that would be a really interesting way to go, because I think they're still working on what the exact plans for the survey will be, right?
Yeah, and no one has taken ownership of binaries yet.
Yeah, that's really interesting.
In the like AGN collaboration, at least. So I think there's room to say something about it, but and interest from the AGN side about like what what cadences are prohibitive for different kinds of science.
Yeah, that's a really good point, because I think there's it's still working out like what order it would do different bands in and things like that. So that could be really interesting.
Yeah, but it sounds like the framework is like you've really made a lot of progress on the framework for answering that question. So yeah, it was a great talk. It was really.
Thank you.
I was actually wondering about the kinds of light curves and signals that Jesse is an expert in, where really long period, you're not really going to get a cycle in the amount of data that we have thus far. Do you think it's kind of really tough? Like, how tough would it be to disentangle a stochastic process from a really long period binary that exceeds the length of your data?
Was this for me or for Dr.?
It was for you.
Okay.
I'm wondering, based on the simulations you've done, whether there's anything. Yeah.
Yeah, that's a really good question. And I think that's something where we might even need to really start playing with matching up the different surveys, like Ting did, for example, with PG1302, because any given survey might not recover an entire period, and we should try that. But once Vera Rubin comes online, we don't want to throw out all that existing data, because it will still be there. I'm not sure if that's what you were thinking, but I've been wondering about this.
Yeah. Okay. Any further questions for Caitlin? Okay, I'm going to be greedy and jump in with one more. Would you mind going back to the 3C66b like 2D frequency plot? Yeah, this one. So this is a really important result that hopefully lots of people recognize. And I wonder also, is the statement not just about the width of the prior here, but also where that prior is overlapping in terms of the features, like that low frequency reduction in sensitivity. Is that the quadratic spin down wall of the PTA where it slopes up?
Yeah, I think it is. So I think really the change frequency is the same as like the bucket frequency.
Yeah.
So I think another important takeaway is that it's basically for the higher half of the frequency range that we can do just as well once we convert to chirp mass. So just converting that bucket shape to chirp mass ends up with this like tilted wedge shape. So yeah, I think it is the same processes. It's just those rescaling. So it's really knowing the distance and the sky location, I think. Being able to search directly in chirp mass that ends up flipping that upper wedge over onto its side.
So maybe I could ask a question. So you pointed out that the what 3C66b is in a sort of bad part of the sky. Are there any speculative supermassive binaries in a better part of the sky? And part B might be, is there a reason then to go search for neutron stars in specific patches or pulsars in specific patches that might be useful for you?
Yeah, I think there are a bunch of people who are pulsar searching experts who are working on this and trying to look more like on that right side of the sky and try and even things out. This is another argument for banding together with other pulsar timing arrays that can potentially see more of the sky, so we can include some more pulsars. As for whether there are any good ones in the good part of the sky, a few of those CRTS sources that I showed here are on a better side of the sky, and I've been contacted by the authors to take a quick look. Unfortunately, I don't think we're quite expecting to detect any of these until some future data sets, but they do exist.
Thank you. Yeah, nice talk.
Thank you.
Jesse, go ahead.
So this may be a poorly phrased question, but let me see if I can figure out how to get my idea across. Thinking about 3C66b, have you developed any intuition for the kinds of things that make candidates interesting to look at, and the kinds of things that matter most in this regard? Like 3C66b is not in a great part of the sky in terms of PTA sensitivity, but clearly you can still do something with it. Have you thought about like the interplay between that and like how, the separation matters, so that you get a stronger signal, or like, I don't know. Can you just talk a little bit about thoughts about what makes a good candidate to look at in that sense?
Yeah. Actually, conveniently, because I'm on this plot, so like they've also shown OJ287 on here, which is also a really interesting supermassive black hole binary candidate. However, that one, for example, is a lot more eccentric and has a much smaller mass ratio. So people have asked whether it's interesting to look at, and it might really not be until we get some more eccentricity methods. So that I think that's one reason 3C66b is interesting. It has a fairly even mass ratio, or at least from that model, and they modeled it as fairly circular. So we do have a good chance of using our existing methods. Of course, it is right near this 2 per year frequency bump, which I think we were worried might affect our sensitivity a little bit. But I think just because it's such a high mass candidate, it's been a very interesting first pass target, because you never know when you're going to be able to hit that mass marker and rule it out or detect something.
Well, thank you.
Yeah.
Terrific. Any other questions for Caitlin? Okay, then as Caitlin said, if you want to follow up, then please feel free to contact her. That was great. Thanks so much, Caitlin. Thanks everyone for attending, and talk to you all soon.
Thank you so much for having me.
Bye-bye, everyone.
Thanks. Bye.